Alright, so in this video, I'm going to be explaining another important paper with the title Maximal Independent Vertex Set Applied to Graph Pooling. By the way, this maximal independent vertex set is a very important topic in graph theory, very classical graph theory in mathematics, in both pure mathematics and applied mathematics. And so they leverage this idea for graph pooling, this paper in 2022 in France. Convolutional neural networks have enabled major advances in image classification through convolution and pooling. In particular, image pooling transforms a connected discrete grid into a reduced grid with the same connectivity and allows reduction function to take into account all pixels of an image. However, a pooling satisfying such properties does not exist for graphs. Indeed, some methods are based on a vertex selection step, which induces an important loss of information. Other methods learn a fuzzy clustering of vertex sets which induces almost complete reduced graphs. We propose to overcome both problems using a new pooling method named MIVS pool. This method is based on a selection of vertices called surviving vertices using a maximal independent vertex set and assignment of the remaining vertices to the survivors. So you see general architecture of our graph neural network. Each block is composed of a convolution layer followed by a pooling layer. Features learned after each block are combined to have several levels of description of the graph. On figure 2, you see proposed graph pooling of this paper. Each node is associated with a score. So a MIVS is computed from which a reduction matrix is derived. You see the evolution of maximum independent vertex set algorithm on a graph from this NCI1 dataset that we use for graph classification. So candidate, survivor, and non-survivor vertices are with different colors that we will talk about. The top K methods, which is one of the important paradigms in graph pooling, one of the ideas, we define the reduction matrix as the restriction of identity matrix to the column indices, these indices corresponding to the surviving vertices. Given a surviving vertex in the original graph, we have this where phi of y denotes the column index of y in the reduced matrix. All other entries are set to 0. The matrix S sub L is called selective since it selects the attributes of the surviving vertices and removes those of non-surviving vertices. Moreover, in this case, rows of S sub L corresponds to non-surviving vertices are equal to 0, and two surviving vertices will be adjacent if and only if they were adjacent before reduction. So we should say that a subset is independent if this holds. And this is a subset of phi such that for any pair, x and y are not neighbors, for example, the elements are called surviving elements. An independent set is said to be maximal when no element can be added to it without breaking the independence property. So when we have this property, it states that each non-surviving element has to be in the neighborhood of at least one element of this group. The elements are denoted as survivors. A maximal independent vertex set is therefore a maximal independent set where the neighborhood is deduced from the edge set. And if you combine 5 and 6, we select surviving vertices like this. And this mirror algorithm is a very, very old algorithm. So they use this idea at the initialization. We assume all PIs are false and QIs are true, and we update it with this equation. But this is important. Now, the uniform random variable plays an important role in the selection of surviving vertex set. We want to modify this variable so that x sub I used in the algorithm is learned and represents the relevance of vertex v sub I. We obtain this last property by using an attention mechanism like in SACPOO, where a score vector is returned by a GCN. So using this score, we select a set of surviving vertices corresponding to local maxima of the function of interest encoded by S. In order to construct our reduction matrix and take all vertices information into account, we need to assign non-surviving vertices. So this equation 8 you see here states that each non-survivor has at least a surviving neighbor. Each non-survivor has at least a surviving neighbor. Assume that the score function encodes the relevance of each vertex. We assign each non-surviving vertex to its surviving neighbor with the highest score. And we obtain a reduction matrix with n sub L plus 1 clusters corresponding to surviving vertices. So finally, the construction of reduced attributes and adjacency is obtained using an average weighted by S from the set of aggregated vertices of surviving vertices. So this MIVS pool may provide a decimation ratio lower than 0.5. So to correct this, we additionally introduce a comp, which is MIVS pool, where we force addition of surviving vertices using top K approach. And they use these data sets like for classification, graph classification, to prove that their idea is better than, for example, better than GPOO or better than SACPOO, just 2% more than SACPOO for D&D dataset. Or for enzyme, you have a more improvement if you compare with GPOO or with SACPOO.